In this lecture, we're going to talk about electrophilic aromatic substitution reactions involving rings other than benzene. You can see here that we have a couple of examples with heterocycles. So heterocycles, as you recall, are cyclic compounds that have non-carbon atoms in there. So pyrrole on the left here and pyridine are examples of heterocycles. And you can see that in electrophilic aromatic substitution reactions with these heterocycles, we can get these reactions to work, and also we have a preference for one product. For pyrrole, we can see that addition at the 2 position is the preferred product, and for pyridine, addition at the 3 position is the preferred product. So let's go ahead and see if we can figure out how these reactions are occurring and why we're getting preference for pyrrole at position 2. So let's draw out pyrrole. And we're going to pretend that we're adding, let's do a generic electrophile, let's just do bromine over here. So of course, in the electrophilic aromatic substitution reaction, we get addition here, and we're going to try this out and see what happens when we add it at 2. Okay, so if we put our bromine in position 2, that means we have a positive charge at position 3. Let's draw out our resonance structures that are possible with addition at position 2. Okay, so that's one resonance structure. And there's our second. See that we have 3 resonance structures that we get when we have addition at the 2 position. Okay, let's do the same thing for position 3. Okay, so now we're going to draw this where we've added the bromine at position 3. And in this case now we're going to have the positive charge at position 2. Now let's look at what resonance structures we can draw. Okay, at this point, you'll notice that if we try to draw more resonance structures, we really are kind of stuck. We can't pull these electrons here down because then we'll have too many bonds to that nitrogen. And if we move electrons around a different way, so if we move these electrons over here, we're adding negative charges and more positive charges. We're really stuck here. So in this situation, what we have is we have 3 resonance structures in the top scenario and only 2 in the bottom scenario. That means that this top approach is going to be preferred because we have more resonance structures, and more resonance structures equals more stability. And even if you compare the resonance structures, notice that, these 2 are kind of similar and that we have a positive charge and a nitrogen. These over here are all octet rule violators. So they're similar in terms of stability. Okay, let's go back and look at our next example. Now our next example, we were going to be looking at pyridine. And notice that pyridine has the preference for the 3 position. Let's draw out our resonance structures for pyridine and see if we can understand why there's a preference for that. Again, we're going to use bromine as our generic electrophile. So we're going to start off with addition at the 2 position. So if we add our bromine to position 2, then that means that we're going to have our positive charge at position 3. And we can draw resonance structures. Okay, so those are our 3 resonance structures for addition at position 2. Let's do the same thing for addition at position 3. Okay, so we were also able to get 3 resonance structures for addition at position 3. Now let's go through and compare these resonance structures. So if you go back and remember from Chem 2300, when we had to determine what contributes best to a resonance structure, let's go look at all of these. So let's see, over here we have a octet rule violator, right? We only have 3 bonds to that carbon. We also have an octet rule violator there and an octet rule violator here. So we have 3 octet rule violations in the top example. And in the bottom example, we also have 1, 2, 3, an octet rule violation in each of our structures. So how do we decide which one is worse? Well, if you'll notice that all of these positive charges are on carbons, except for in the top example. So this example here has a positive charge on a nitrogen, and a positive charge on a nitrogen is worse than a positive charge on a carbon. Remember that we like to have positive charges on more electropositive atoms. And this is going to be why we do not see a preference for position 2. Instead, we'll see our preference for addition 3. Now let's talk about diazonium salts, and they can actually be electrophiles, just like things like Br+ can be electrophiles. So diazonium salts, if you recall, remember that we make those from amines, and you could see in this example a diazonium salt that was generated. So here's our diazonium salt. And what's happening here is the alcohol is an electron-rich group, and so you have an electron-rich benzene ring. And the benzene ring is able to do electrophilic aromatic substitution with the diazonium salt. And you're ending up with an azo linkage. In the bottom example, we have another one where we have an electron-rich or electron-donating group on our benzene ring. So in the top, it's a phenol. In the bottom example, it's a nitrogen. And these are electron donating, making the benzene ring electron rich and activating it for electrophilic aromatic substitution. so it can react with that azo group. If you're trying to think about, okay, how is this reaction working? Remember that our phenol, or in the bottom case, our amine, are electron rich, and then so we can get attacked that way. So if you imagine kind of us drawing out the arrows, we have our very positively charged diazonium salt, and we would add just like that. Okay, so that would be our addition of the electrophile step, and then there would also be another re-aromatization step that you would have to do. In the bottom example, we can show those electrons there attacking the diazonium salt and the electrons going to the positive charge. So that's how that bottom one would work. You can see the detailed synthesis in this slide, right? Again, we have an electron donating group, and that's going to make the benzene ring very electron rich. So we are attacking from the benzene ring. So the electron rich benzene ring is attacking our electrophile, and electrons are going on to the positive charge. This is also breaking down the steps. So you can see our re-aromatization step happening here in step 2, where our generic base in solution is pulling off a hydrogen and reforming our benzene ring. And when you're thinking about what that base might be, it's going to depend on the reaction conditions. So in this previous example, notice that here we have HCl and water. So it's highly likely that water could be our base in this particular example. Okay, so that wraps up electrophilic aromatic substitution. Our next topic will be a nucleophilic aromatic substitution.